Chemical equilibrium, part 1. What is equilibrium? Okay, so let's start our discussion of equilibrium with a question. We're going to compare two sealed containers here. One of them has water in a sealed container at 25 degrees C. And we're assuming both of these containers are in a room at 25 degrees C, so room temperature. Now the other container holds ice cubes at 25 degrees C. How would we know which system is at equilibrium? Well, let's think about this for a second. So we have our water in a sealed container at 25 degrees C. If we were to just go away and come back, that container would basically look the same. That system is at equilibrium. So nothing is macroscopically changing. Now, think about what would happen to our ice cubes in a sealed container at 25 degrees C. You might be thinking that something would change there. We would notice a change. And you'd be right, and this system is not at equilibrium. So this brings us to one of the central concepts in equilibrium, and that is that a system has reached equilibrium when its macroscopic observables have stopped changing. So when the types of things that we can measure, such as pressure, temperature, volume, density, color, all of these things are macroscopic observables, and when they stop changing, that means the system has reached equilibrium. So let's go back to our ice cubes in a sealed container. Now, if we just let time pass, our sealed container will hold water eventually at 25 degrees C. So basically, this system would come to equilibrium, and macroscopic observables have stopped changing. We know that macroscopic observables stop changing when the system is at equilibrium, but microscopic processes are still going on. Now, what does that mean? So to answer this question, let's go ahead and think about the equilibrium vapor pressure that we talked about earlier in this course. We have molecules in the liquid phase that continuously vaporize and condense in a closed container. So we have liquid water molecules, gaseous molecules, okay? So they continuously vaporize and then condense, and vaporize and then condense. And this equilibrium vapor pressure stays the same. It stays constant. So that pressure isn't changing. And that means that the system is at equilibrium. So the partial pressure of the gas is constant at equilibrium. The rate of evaporation is equal to the rate of condensation in this closed system. Okay, so let's look at another system. So now we have a reversible reaction where we have nitrogen dioxide forming a dimer, dinitrogen tetroxide. And this system is in equilibrium. Now the forward reaction is two nitrogen dioxide dimerizing to form dinitrogen tetroxide, and then the reverse happens. The dinitrogen tetroxide splits apart into the nitrogen dioxide molecules. Even though this system is at equilibrium, this guy right here, okay, so the rate of each process going on, the dimerizing and the splitting apart, the rates of those processes are equal. They are occurring. So even though it looks like nothing's happening, we're continuously forming the dimer and splitting apart, forming the dimer, splitting apart, forming the dimer, splitting apart. What happens to the partial pressure of each gas once this system reaches equilibrium? And the answer is that the partial pressure of each gas remains constant. Let's see how this works. So let's do two experiments. We're going to start with all nitrogen dioxide in one container, in one experiment, and we're going to start with all dinitrogen tetroxide in the other. So experiment 1, we're going to put 1 atmosphere of nitrogen dioxide in a 1 liter flask at 298 K. Now notice both these experiments are at the same temperature, they're in the same size flask. So the only thing that's different is we're going to start with all reactant or all product. Okay, and we're going to compare the final partial pressures for these two experiments. Okay, so here's experiment 1. We are going to start with all nitrogen dioxide. And in time, nitrogen dioxide is going to dimerize. So we're going to gradually build up a partial pressure of dinitrogen tetroxide, and the partial pressure of nitrogen dioxide is going to go down until it reaches a constant value. And that's going to happen for both of these. So this nitrogen dioxide goes down in partial pressure to a certain value, and dinitrogen tetroxide goes up in value to a certain amount, a certain partial pressure. After this point, even though I'm not showing it, this is just constant. It just doesn't change anymore. All right, and so notice that the final partial pressure once the system comes to equilibrium for nitrogen dioxide is 0.5 atmospheres, and it's 0.25 atmospheres for dinitrogen tetroxide. Okay, so now let's do experiment 2, and let's start with all dinitrogen tetroxide. Now, we're going to start with half an atmosphere. All right, we want the same amount in our system. So we are going to start with half an atmosphere of dinitrogen tetroxide, and that partial pressure is going to go down as the partial pressure of nitrogen dioxide builds up. Look at the final partial pressure of these gases after we start with all dinitrogen tetroxide. It's the same. So nitrogen dioxide ends up at 0.5 atmospheres, and dinitrogen tetroxide ends up at 0.25 atmosphere. So when the equilibrium state was reached, when this system came to equilibrium, notice that it didn't matter if we started with all reactant or all product. So we started with all nitrogen dioxide and we got to the same place. We started with all dinitrogen tetroxide and we got to the same place. Those equilibrium partial pressures of those gases arrived at the same distribution or the same state. And so in the end, we ended up with 0.50 atmospheres nitrogen dioxide and 0.25 atmospheres dinitrogen tetroxide. Didn't matter if we started with all reactants or all products. One of the central equilibrium concepts is that at equilibrium, there is no change in macroscopic observables. So that means it looks like nothing is happening. However, on the microscopic level, on the individual molecule level, things are still happening. We just can't see or measure them macroscopically. The next central equilibrium concept is that the final equilibrium concentrations or partial pressures of reactants and products is completely independent of the initial concentrations or partial pressures of the reactants and products under a given set of experimental conditions. So if we start with all reactants or all products, the reaction still goes to the same distribution of reactants and products. Okay, so that's a central concept. We can start with 100% reactants, 100% products. The equilibrium state will be the same under a set of experimental conditions. Next up, the relationship between kinetics and equilibrium.